Welcome back to ECE 501B. Just as a reminder, Monday is a holiday, and a week from today I won't be here, so you don't have to worry about class physically in this room, but stay tuned. I probably will give you information and material to work through or to examine for next week. Project deliverable number 1 is due a couple of weeks from today, and homework 7 and 8. 7 is 3 weeks from today, so that tells us how long we have, and homework 8 is a month away, and then our final is less than 5 weeks away. That's how close we are to finishing up the semester. Your deliverables, main deliverables for the project, are due then, what did we just say, in 4 weeks at the last day of class. Today what I want to do is first review basically terminology and then restate the complex spectral theorem. Remember, we're talking about the spectral theorem on two different fields, the real field and the complex field, or the field of complex numbers and the field of real numbers. The complex we talked about last time. We'll just repeat that or state that. Then we'll review the Cauchy-Schwarz inequality. We'll talk about completing the square, and that will then allow us to move into a couple of lemmas prior to stating the real spectral theorem. So we didn't need all of that to do the complex spectral theorem, but we do need more conditions in play to talk about the real spectral theorem. And these spectral theorems are really telling us how do we, or when can we have nice matrices? When can we have matrices that are equivalent to diagonal matrices? That's what these spectral theorems are talking about, and we'll summarize those for the two different scenarios, real and complex fields. Then we'll start talking about two other concepts dealing with operators. We'll talk about positive operators, and those you can think of as ways of scaling, either reducing, a positive number could be 1/2, so we could reduce or we could increase, enlarge with a scale factor of 3, a scale factor of 10. Think of these positive operators like we're scaling something, and we'll talk in terms of definitions, theorems, examples, and proofs. Then we will introduce, if we have a positive operator, you can think of that like a positive number. We can take the square root of that. We can now have square root operators. And in addition to thinking about scaling operators, we can also have isometries. And isometries, think rotation. And now if we can rotate and expand or rotate and contract, we should be able to get anywhere we want with an operator, and that's what we're trying to come up with, is how do we scale and direct, or scale and rotate, or how do we represent or decompose operators or maps into those operations and go from there. So that's what we're hoping to be able to accomplish. Some recaps. We want to not forget what we mean when we say a linear map is an adjoint. That just means that we can slide those linear operations into the second slot that were in the first slot. So there's the relationship between the linear map and its adjoint, and those relationships are tied or connected through the inner product. If we have an operator that's normal, then that means that the operator and its adjoint commute. Or t dagger is equal to t dagger t, and an equivalent way of thinking about a normal operator is that it preserves norms. Given any vector v, then the norm of tv is equivalent to the norm of t dagger v if that operator is normal. And we also have a map being self-adjoint, or an operator being self-adjoint. That means that T is equal to its adjoint. Here's the complex spectral theorem that I'm sure you all ran home and couldn't wait for the video, or actually the notes, to be presented, but I did follow up with the final steps of the proof. But now suppose that we're on a complex inner product space, V, and T is a linear operator on that complex inner product space. Then if that's the case, the following statements are equivalent. 1, T is normal, and we know what that means. That's in curly brackets in blue. T dagger is equal to T dagger T, or T commutes with its adjoint, or it's norm preserving between T and its adjoint. If it's normal, then we can think, oh, this vector space has an orthonormal basis, and we need the inner product for that to be true, or to exist. We need to be able to think about lengths. So now we've normalized these basis vectors, and we've orthogonalized them, or we can if we have a normal operator, and that basis is really in the direction of these eigenvectors of the linear operator T. If that's the case, if we have orthogonal and normalized eigenvectors, we can also diagonalize that matrix T. So any of those are equivalent. You say T is normal, you can now just put these other two in your back pocket and say, oh, I also have these as a consequence of my operator being normal. We need to look at four things if we consider the lemmas as two distinct pieces. Let's review the Cauchy-Schwarz. We'll talk about completing the square and how that, now thought of in terms of real numbers, can be generalized to operators, so that we can now think of completing the square in terms of operators. Then we'll introduce lemmas 26 and 27, and then we'll state the real spectral theorem. Just as a reminder, here's Cauchy-Schwarz. That says that the absolute value of the inner product, remember the inner product is a scalar, so that can be a complex number, but we know how to find the magnitude, or the absolute value, or the modulus of a complex number. That's less than or equal to the length of each of those vectors inside the inner product. And based on our knowledge of absolute value, we can now put or bound that inner product with two limits. A lower limit minus the norm of those two vectors multiplied together, or less than or equal to the norm of those two vectors. We'll actually use the left-hand side later to show how we can now obtain a lower bound on a property, or on an expression. So we'll use the Cauchy-Schwarz, the left side, in our discussion. So now let's talk about completing the square, and I know that this may go back many years, so let's just kind of work through it so that we feel comfortable with it. Suppose we have the following expression. Where the expression is our normal quadratic expression, x squared plus bx plus c. And it's monic, meaning we've normalized the leading coefficient to 1. So we don't have to have an ax squared plus bx plus c. A is 1, so now we have this x squared plus bx plus c. And now let's just remind ourselves of how we can view that in terms of completing the square. And if you wanted to think about this, you could say, oh, let me just plug in different values of b and c and x, real values, and see what that curve looks like. We know that it's what? Going up at the extremes. But what's it doing in between? Is it actually going through 0? We want to actually bound it above 0, which means that we don't want really real roots in this quadratic. So when we start completing the square. So here's our note. If I now look at x plus b over 2 and square that, I apologize, maybe I'm insulting your intelligence, but here's what we have, right? So I'm wanting us to try to just keep track of what's going on, and now if I multiply that out, I end up with that. And I really am wanting to somehow make the upper expression, x squared plus bx plus c, look like some squared quantity, or at least something that's positive. And here I can cancel the 2, so I really do have x squared plus bx already sitting there. And what I now need to do is rewrite that so that I have it equal to c. Or if I now start with x squared plus bx plus c, I can now say, well, that's x squared plus bx, and then let me say plus c, and inside that I'm going to just add 0. And the 0 that I will introduce is created out of 2 pieces associated with b over 2 squared. So now I have plus b over 2 squared minus b over 2 squared. So I haven't really done anything magic. I've just really allowed myself to complete the square. This is just 0, so I'm adding 0. But now I can view that as a nice square of x plus b over 2 quantity squared. Or I can now say that x squared plus bx plus c is equal to x plus b over 2 quantity squared plus what's remaining, which is c minus, and let me go ahead and multiply that out, b squared over 4. And when am I assured that that will be greater than 0? Under what conditions can I force that x squared plus bx plus c to be bigger than 0? And that's why I tried to sort of create that squared quantity, x plus b over 2. That takes care of quite a bit of the expression. But now, as long as I can ensure that this, when this c minus b squared over 4 is bigger than 0, then I can be assured that x squared plus bx plus c is bigger than 0. And this is true for c bigger than b squared over 4. Or if I multiply both sides through by 4, I can now say as long as 4c exceeds b squared, I'm going to have that quadratic always bigger than 0. So let me just state that. Therefore, when b squared is less than 4c, then I can conclude that x squared plus bx plus c is going to be bigger than 0. And if I actually now applied the quadratic formula to that, you remember what's underneath the radical. B squared minus 4ac, and we said a was 1, so it was b squared minus 4c. And when was that complex? when that was less than 0, or now when b squared was less than 4c. And that's what we have here. And that means that we don't have any zeros or any real terms, any real crossings of 0 in that x squared plus bx plus c. So it's bigger than 0. Since x squared plus bx plus c is bigger than 0, we could also say, or x squared plus bx plus c is an invertible number. Pardon? What does that mean? So if I tried to divide by 0, I'd have problems, right? So as long as I'm guaranteed that this is bigger than 0, I can divide by it. It's invertible. So that expression now has an inverse, as long as it's bigger than 0. That's all that means, or that's what I'm trying to say. i.e., it is not 0. And that's, what am I assuming? That's when x is real and these b and c's are real. So when those are real and it's such that b squared is less than 4c, then I'm guaranteed that x squared plus bx plus c is always positive. I can then divide by it. So what? Well, now we can use this power that we have, that we now possess, to think of these real number things, issues, concepts, or apply those to operators. Now that we have this understanding of this polynomial in x, where x is a real number, what did we remember, or what can we do when we apply these operators to those numbered quantities? So what happens when we replace the real number x what was a real number associated with in terms of an operator? Do you remember? If I had a linear map, we said, oh, that's just like a complex number. The adjoint was its conjugate. If we wanted the operator to equal its adjoint, then it was self-adjoint, wasn't it? And we needed that to be real, or that would be a real number. So what happens when we replace the real number x with a self-adjoint operator? And all we're doing is we're recalling the analogy between these numbers and these operators. So recall the analogy between real numbers and self-adjoint operators. That's what we're using now. And that now allows us to actually state a lemma. Lemma 26. And this lemma is concerned with invertible quadratic expressions. And the lemma goes as follows. Suppose T is a linear operator, and it is self-adjoint. And B and C are both real and are such that B squared is less than 4C. Then this quadratic expression T squared plus BT plus CI is invertible. And that's all because we can sort of think of these real numbers like self-adjoint operators. Let's now show that or prove that. First, assume that we have B and C being these real numbers such that they satisfy the relationship that we need, which is B squared is less than 4C. And we'll just take a vector V to be non-zero. We have a non-zero vector arbitrary in our vector space V, and we have two real numbers B and C such that B squared is less than 4C. And now let's look at the inner product of T squared plus BT plus CI applied to this vector V, inner product with V. And let's see what we can say about that. What's that going to produce? A scalar, right? So now it'd be nice if we could show that that scalar is positive. So now if I create something a little bit cleaner, meaning let's get rid of that quadratic expression and try to write it as maybe three inner products by doing additivity and homogeneity, and I'll just call that linearity. So if we remember that we can use linearity of the first slot, then we can say that that left-hand side is now equal to T squared V, V inner product, plus, and let me go ahead and do the homogeneity, B times TV with V, plus C V comma V inner product. Is that okay? So all we're doing is applying homogeneity and additivity, or what I'm reducing to just one phrase, linearity of the first slot. And now we can separate that T squared. T squared is T applied to T. So now we have two operators in the first slot. Let's move one of those to the second slot. So we have T times TV. Let's move that first T to the second slot. That means what? It needs to be its adjoint if it's in the second slot. So now the definition of the adjoint allows us to rewrite that as TV T dagger V plus B TVV plus C VV. Isn't it fun what we can do now with all of this knowledge? And what did we assume up here in this lemma? We assumed T was self-adjoint. So that now anywhere we see an adjoint, we can get rid of it, can't we? So now we can say, well, since we have this operator being self-adjoint, we can rewrite that first inner product differently. We can just say TV inner product, TV inner product with itself plus B TVV plus C VV. And now we have a lot of similar things in the slots, don't we? And when we have first slot and second slot being the same, we can view that as a norm, or the norm squared. So now the definition of the norm says that the first one says, oh, that's just the norm of TV squared. The second one I can't simplify because the first and second slot aren't the same. So now I have B times the inner product of TV with V, but I can rewrite the third term as the C times the norm of V quantity squared. So I'd like to have this a little bit cleaner. I have TV and I have V as norms, or norms squared. I can actually get those same norms on that centerpiece if I use Cauchy-Schwarz. So now I want to find a lower bound on this. I can now, let's just say I take the absolute value of B, and now this is going to be greater than or equal to, using the Cauchy-Schwarz, I'm not going to touch the first one or the third one, but now I can say this is now the absolute value of B, norm of TV, norm of V, plus C, norm of V, plus C times the norm of V squared. And you probably weren't, well, now can you see what I want to do? This is like x squared kind of plus bx. It's now minus bx plus c, but I can complete the square with a minus bx. So now I'm going to complete the square with that mess on the right, because I have everything now as just a combination of numbers. B is a number, C is a number, etc. So now completing the square allows me to say that that's greater than or equal to, and now I have TV, that norm squared, and I'm viewing that like x, so I now have TV minus B TV over 2 squared. I'm writing too big. Yes? So where did the negative sign come from? That came from our Cauchy. Whoa, boy, I shouldn't have been doing that. Now I'll never get back. That came from here. Cauchy-Schwarz. So that was why we were trying to review that. And who knows if I'm ever going to recover from that disaster. Tried to go too big. Are you kidding me? This is testing my patience. So now I think I'm back to 65. Where was I? Oh, I'd even erased what I tried to do with completing the square. It doesn't even want me to complete the square, so I'm going to have to do it again. No more questions. No, that's fine. But now I have TV, there's x, minus whatever I need up there, which is B, and I don't want TV there because I'm going to pick it up, so I can make that a little bit smaller. That's why I had to do that. there. So that now I'm really capturing this middle piece in the linear piece when I square that term. And what I have to now pull out is what? I'm now adding b squared v squared over 2 squared. So I need to take that away. So I now am saying I have minus b v squared over 4 plus c v squared. Is that okay? And now I can combine those two terms on the right and say that that's going to be bigger than TV minus b v over 2 squared plus the quantity c minus b squared over 4 times the norm of v squared. And this piece I can be assured of being bigger than 0 when the first squared quantity is bigger than 0, but now I simply need to make sure that c minus b squared over 4 is bigger than 0. Or I now need c to be bigger than b squared over 4, or b squared less than 4c. And remember, b and c were real. So I have the absolute value of b, that's squared is the same as b quantity squared. So that now that's what I assumed, and now that's the only assumption I need in this expression to make sure that it remains positive. And now what did I start with? I'm going to do this slower. But now that's what I started with, that inner product, and now I've shown that that is bigger than 0 as long as 4b is less than, no, 4b, b squared is less than 4c. I can foresee the future. No, I can't. But b squared is less than 4c, that then tells me the following. That allows me then to say that this quadratic expression inside the inner product of t squared plus bt plus ci applied to v, the inner product is positive. Now we need to put on our different sort of thinking process and say, well, what does that mean? If this is always positive for every v was arbitrary, and we picked it out of our vector space, and now we're saying I have this operator which when I apply it to v, and then I put that with an inner product with v, it's always positive. What's that allow me to say or conclude? What can I conclude from that? When would this not work? When could something, when hit with a vector, maybe produce a 0? That's now an operator times a vector. What property does that vector enjoy if that operator times the vector gives me 0? If I had ax equal to 0, what do I know about x? It's in the null space of A, right? Now I'm saying that no matter what the v is, I cannot have the first slot being 0 because this has to be bigger than 0. Or in other words, do I want to leave that in there or do I want to erase that? I'm afraid to erase now. Afraid to do anything. We'll see. Be brave. What's that say? Therefore, this vector v cannot be in the null space of that quadratic expression. V cannot be in the null space of t squared plus bt plus ci. And v was any vector. So now if v is any vector, what's that tell us about that operator? If it has a trivial null space, it does not possess a non-trivial null space. That means it's injective, isn't it? And it's an operator. So now we can go back to that one theorem that makes this equivalence between injective, surjective, and invertibility. So now we know, or we can say, therefore, since this has a trivial null space, that operator, then t squared plus bt plus ci is injective. And now from that earlier result on operators relative to how we can now say that these are equivalent statements, it's surjective and it's invertible. So now we know that t squared plus bt plus ci as an operator is invertible. And I think that's what we were setting out to show. That was our lemma. That was lemma 726. So now let's state the next lemma, which is 727, dealing or labeled as self-adjoint operator or self-adjoint operators have eigenvalues. Here, this lemma says suppose that again, well, now let's not allow our vector space to be trivial. Let's assume that the vector space is something other than the 0 vector. So now we have a non-trivial vector space, and this linear operator t is self-adjoint. Then t has an eigenvalue. And I'll just say, let's see the text for that proof. But now, if we have a self-adjoint operator, we're assured that it has an eigenvalue. Just like if we were dealing with a complex vector space, any operator there had an eigenvalue. We weren't assured of that when it was real. But now, if our operator is self-adjoint, we do have an eigenvalue. That's what this is giving us. Now we're ready to state the real spectral theorem, and that's Theorem 29. And this says, suppose we're dealing now with a real number field, f is r, and t is an operator in a vector space over that field. Then the following statements are equivalent. First, T is self-adjoint. And that just says that T is equal to T dagger. If T is self-adjoint, then V, this vector space, has an orthonormal basis consisting of eigenvectors of the operator T. So before, when we were on a complex, it needed to just be normal. Now it has to be self-adjoint. C is that T has a diagonal matrix representation with respect to some orthonormal basis on our vector space V, or of V. And again, we'll put that back. Yes. Is what? What can we say about T being normal? So now, since it's self-adjoint, it's guaranteed to be normal. If it's normal, we don't necessarily have self-adjoint. But now we're guaranteed that it's normal, since it's self-adjoint. So let's just sort of remind ourselves of what we now have available to us. Here's a summary of these spectral theorems. And really, you're maybe wanting to think, what linear operators allow me to think about in a particular basis having diagonal matrices? That's sort of what you're keeping in the back of your mind. A vector space V has orthonormal basis of eigenvectors of this linear operator T, and T can be diagonalized if and only if, in the first case, this vector space is actually a complex inner product space and T is normal, or the second case, B, V is a real inner product space and T is self-adjoint. So that's now how you can summarize these spectral results. Is if we have T being normal, then if we're on a complex inner product space, we can diagonalize a matrix representation of T. If we're on a real inner product space, then we need T to be self-adjoint, which is stronger than it being normal. So that tells us what we have to have in place to have sort of these nice matrices. A lot of zeros is a normal operator or a self-adjoint operator, depending on what inner product space we're living on. So now that that's available to us, let's now maybe look at how we can think about more general maps or operators. And one way to start is to think about scaling, or what are now we will now refer to as positive operators. And again, what I like to think of is of the concept or notion of scaling when we're thinking about positive operators. How do these contract or expand a vector? Here's the definition. An operator T on a linear operator T on a vector space V is positive if T is self-adjoint and the inner product of TV with V is greater than or equal to 0 for all vectors V in our vector space capital V. So that's the definition of a positive operator. It needs to be self-adjoint, it needs to be equal to its adjoint, and the inner product of TVV needs to be greater than or equal to 0. Note, if our vector space V is complex, then this linear operator T is self-adjoint when this inner product TV with V is in fact real. So that's a scalar, and if we're dealing with a complex vector space and T is self-adjoint, then we actually, when we start taking these inner products with TV and V, we'll get real numbers or real scalars. Here's a justification of that note. here's a fact that we will remember until 5 weeks. Isn't that when we're done? Didn't we say that we're 5 weeks minus a day from the final exam? So now the inner product, one property of that is what? Yeah, there's a lot of properties, aren't there? There's 5 of those. But what was the last one? What happened? What kind of symmetry does it enjoy if we flip things between the 2 slots? Then it's conjugate symmetry, isn't it? So the inner product is conjugate symmetric. That means then that if I have the inner product of TV and V, that's equal to, and now you're going to be upset, but I'm going to switch my notation just for this justification. I'm going to use an overbar for complex conjugate because I'm going to have a lot of overbars instead of starring, and you know me about stars. I'm not very good with stars. So now let me say that this is our definition of conjugate symmetry. I've switched the order of my vectors in the slots, and now I'm saying that this is the complex conjugate operation. That overbar. Just for this note. Okay? So now if this scalar, the inner product of TV with V, if that's real, then what does that enjoy? If I now looked at TVV and I took the complex conjugate of that, what is that equal to? If that inner product is real. If I conjugate a real number, what do I get back? The real number. So this is just TVV's inner product. We're okay there? So now let me play a little bit with these inner products and the conjugates. So now if I have TV and V and I perform the complex conjugate, by the conjugate symmetry, what do I know that equals? Is that right? I switch the slots and I conjugate it. But now what happens when I conjugate a conjugate? I go back to what I started with, so now I can say that that's VTV. Is that okay? And now what am I now allowed to conclude? I can say that the inner product of TV and V is equal to the inner product of V and TV. Because now I have the same thing on the left-hand side of both of these, and I can now equate the right-hand sides. Therefore, I can say that TVV inner product, that was the top one, is equal to the inner product of V and TV. That's from this and that. But now that allows me to say something if I remember, and since TVV, if I now use the conjugate, if I applied the concept of an adjoint, what would that equal? V T dagger V. And now I know that TVV is equal to that, right? So now, and since this last equality is true by the definition of the adjoint, now I can, I don't know what I'm wanting to do, but I'm going to mess things up, I'm sure. But now what I want to do is realize that I can say that those two operations are the same. So then T is equal to T dagger, or T dagger is equal to T. And I think that's what I was wanting to show here. With T being self-adjoint, then this inner product is going to be real. And now I've shown that if it is real, I have to have T equal to its adjoint. So now let's look at some examples of positive operators. And luckily we don't have to go back too far. Remember in the proof of lemma 726 with this linear operator T, when it was self-adjoint, and b squared was less than 4c, that produced a quadratic expression that was positive. So now the proof of lemma 726 with t self-adjoint and b squared less than 4c produces a positive operator. So there's one example of a positive operator. You give me a self-adjoint operator T, I can now build you a positive operator as long as I make sure that b squared is less than 4c via this quadratic expression. What's another example of a positive operator? Every orthogonal projection is positive. So now if you project, remember what we talked about before, in this room, now I give you a point in this volume. That now creates a vector. If we want to project that orthogonally onto the floor, that orthogonal projection now would be a positive operator. Those are some examples. Now we can define square roots if we have positive operators. Here's definition 733. Dealing with square roots. Suppose R is a linear operator on our vector space V. Then we can say that that is the square root of t that's also on this linear operator on the same vector space V if we apply r 2 times in succession, or r squared, and that's the same as t. So r is the square root of t if r is t. We apply r twice and we get t. What are some characteristics of positive operator? Or what's a characterization? And that's now Theorem 35. Suppose now we're given a linear operator t on a vector space, then the following are equivalent statements. We can say t is positive. And we know what that means, don't we? I hate to do this, but I'm going to. What did we say it meant for an operator to be positive? I thought we said that somewhere, didn't we? An operator t is positive, here's the definition, if it's self-adjoint and the inner product of tvv is greater than or equal to 0 for all v. That gives us our positive operator. So now t is positive, and that is equivalent to saying that t is self-adjoint and all of its eigenvalues of that linear operator are non-negative. We're not saying they're all positive, so some can be 0, and it will still have a positive operator. Bless you. C. T has a positive square root. So if t is positive, then we can actually factor it, so to speak, into pieces, where those pieces now form a positive square root. D. T has a self-adjoint square root. Enough already with these equivalent statements, but this is, I guess, good. We're having a lot of them with t being positive. Now E says there exists an operator let's call it R that's a linear operator on the same vector space such that we can write t as r dagger r. So we have a lot of equivalent statements about positive operators. Let's just look at some positive in terms of matrices so we can kind of wrap our minds around all of this stuff. So let's look at some examples with matrices. And now you're going to have a week to think about this, but I'll give you some other stuff in between. But the next time we meet, wow, is the Monday of Thanksgiving break, right? When we meet in person. So here are some examples of... Did I hear applause? First time I've ever had applause in a lecture, and it wasn't because of the lecture. Oh man, that hurts. Square roots and positive matrices. One. Suppose T1 is that. What are the eigenvalues of T1? 1 and 0, right? They're on the diagonal. This is upper triangular. It's lower triangular. It's diagonal, isn't it? So T1 has its eigenvalues on the diagonal. One square root for that, this will throw you for a loop, is that. No, I'm kind of teasing. Or could we also do the following? Could I now say that R times R is going to give me, or I'm sorry, R1 hat times R1 hat is going to give me T1. So there is a positive matrix T1 and some square roots. 2. T sub 2 is now 0, 0, 1, 0, 0, 0, 0, 0, 0. What are the eigenvalues of that bad boy? 0, 0, and 0, right? It's upper triangular. Our eigenvalues are on the diagonal. One way to produce that from a product of two of the same matrix is that, R2. And remember how we can multiply. If we now have what's the first column? It's 0 times all of the first 3 columns. So the first column is 0. The second column is going to be a copy of the first column. Is it clear what I'm saying? I'm stepping through these linear combinations associated with these 3 columns. Here, I'm basically saying 0 times the first column plus 0 times the second column. So here's the first, here's the second, and there's the third. I scale those with 0, I'm going to get 0. If I now look at the second column of my product, that's going to be formed by taking 1 and weighting the first column. And the first column was all zeros, and then I weight the other 2 columns with zeros. So this is going to be 0, 0, 0. And my third column in the product is going to be based on the third column of my second matrix in the product. Says, oh, scale the first column with 0. Scale the second column by 1, and scale the third column with 0, and the second column. And now do you see that R2 times R2 gives you T2? So you can have sort of interesting behavior from positive matrices and their square roots. What's another one? Suppose I now say T3 is a really challenging matrix, the identity matrix. If that's the case, what's R3? So now R3 times R3 gives me T3. So that's kind of weird, but it's true, right? It's 1 times 1 gives me 1. Another way of thinking of it. And we'll be really sort of thinking that way when we start talking about isometries. That will sort of look like ones, these rotations. Now we're dealing with positive operators, which are trying to think of these as being like scaling factors. So that now I have, what are the eigenvalues of T sub 4? 2 and 3. So that now R sub 4, I could make that several different ways. But do you see that if I had that on the diagonal, either plus or minus the square root of 2 and plus or minus the square root of 3 on the other diagonal term, that I could build T4? What about T sub 5? Suppose this one now is something that's not diagonal, but yet it's 3 minus 4 minus 8, 11. And now, if I take R5, that equals minus 1, 1, 2 minus 3, I can form that product. And again, I said you have a whole week to be doing this. You can now multiply that 2 by 2 with itself and hopefully see that that equals T5. We could also say, well, what if I started with the same matrix that I had for T5, but now I wanted to create a different combination of two matrices that yield the same. What if I have 1, minus 1, minus 1, 3? That's a little different, isn't it? And in this case, if you found or looked at, I hope, if I've not made too many typos, the eigenvalues of R5 are actually minus 0.2679 and minus 3.732. And the eigenvalues of R6, and remember, R5 times R5 gives me T5. R6 times R6 gives me T6, which is the same as T5, but now the eigenvalues of R6 are actually the positive versions of the eigenvalues of R5. Yes? I don't know. Am I sure that R6 is right? So let's look. So let's take, darn, we're not out of time. So let's look. R6 is 1 minus 1 minus 1, 3. So now if we take the very first element, it's going to be 1 plus 1. That's going to give me 2. What's that? 3? Whoa, what happened here? Oh, yes, of course. I didn't write down. I knew that I would make a typo. This should be a 2. Does that make you feel a little bit better? So now if we made this a minus 2, is that what I said? Yeah. So now let's make that a minus 2. And now what do we have? Now we have 1 plus 2, or a 3, and we have a minus 2 minus 6 minus 8. Oh, good. And what's in the second column? We have a minus 1 minus 3 and a 2 plus 9, or 11. Is that right? Okay. Is that better? I knew that I would have some kind of typo. Or, yeah, I can't even read my own writing. That was supposed to be a minus 2 in the 2-1 entry. So we'll pick up at that point quite a while from now, but stay tuned. I'll try to give you information to work through or work with when we're not in physical contact. Okay?